Hello guys, welcome to Ask Raghulan. Today we're going to see an interesting topic, which is a project which is nicknamed as Japan's Golden Chamber, and this project is also called as Super-K. So why this project is in news and so what is happening around it, let's go through some of the things. Alright, so now this project is called as Super-K because it's named as Super-Kamiokande. So that's actually the name they have given in Japan. So what this project is about researching into subatomic particle called neutrino. If you heard of this term, it's basically recent news. Several countries are investing a lot of money into neutrino researches. So what is this neutrino and why people are investing on this research and what we get from that? So if you look at neutrino, they are subatomic particles. So what does it mean? So subatomic particles are very tiny. So you know how big is an atom. So the atom has got a very small object, small elements called electrons, protons and neutrons. So these neutrinos are 1 in a millionth of the mass of an electron. So as you can imagine, it's very small and tiny objects. And these objects are considered comes in 3 different flavors. So one is electron neutrino, another one is muon neutrino, another one is tau neutrino. So these are the 3 different flavors of neutrinos that we have. There is also some research going on to unearth some more, I think 4th flavor of it as well, some sort of a different version of it maybe. And so now these neutrinos, why they are called subatomic? Not just because they are very small. If you actually see these neutrino particles go through our actual bodies right now as we speak, and they actually go through without even interacting with any of our atoms and molecules in our body. So that's how much tiny they are. To give you a perspective, sun releases so much of electron neutrinos every year, and these objects go past Earth but they don't even see Earth. So that's how these neutrinos interact. So these are very elusive objects in the universe. So it's very hard to detect them, very hard to actually see what they do and what is the purpose of it. So these neutrinos, if you actually consider this as neutrinos firing from one end, if you actually keep stacks and stacks of steel and lead for, let's say, 1 light year, so that's how long you keep the depth of that material, and if you actually put through the neutrinos will get through the entire stack of steel or lead without even interacting with any of those atoms of those objects. So the neutrinos don't really see other matter, so that makes it more elusive. So why do we need to do research on this? What is the purpose of it? So now, first thing is dying stars. So whenever a star dies, it becomes supernova. So when it becomes a supernova, at the end of supernova, it actually collapses to a black hole. And you know what happens when there is a black hole nearby you? It sucks everything into it and it destroys it. So now these events happens in several parts of our universe. So luckily we don't have anything close to our solar system, but remember there was actually news, people say that could be a possibility that there could be a black hole near to our solar system. But anyway, so that's another story to take away. So now these dying stars, they release lots of neutrinos when they about to die and once they died. So these neutrinos get released in a whole lot of quantities. So these supernovas contribute to the black hole. So now why do we study it? These studies will help us understand or even create a sort of like an early warning system whenever there is a star that is going to collapse. So now this would actually be helpful, let's say for the future generations, or even probably might be in our generation, in our lifetime as well. We'll see actually if there is anything that going within our galaxy, so where there is any star that is going to die, so that we can keep watch out for it and we can learn from it. Because those instances so far, if you look at history, we have not recorded an event of dying star. We only know once after it died. So the process of it when it starts is very important. It actually helps us to understand how the Big Bang worked and how the universe works, how the universe is expanding, and what is the age of the universe. A lot of these questions could be answered through that. So now these are the reasons why people are investing into neutrinos. So now let's look at these neutrinos a bit further. So now This project Japan has initiated in 2004 is called Super-K. So this Super-K is considered of two portions of it. So one is the Super-K, and another one is T2K experiment. So that whole thing is called as T2K experiment. So now the Super-K is basically a chamber, and this chamber is 15 stories high. It's a very, very tall chamber. It's like a multi-story building. So this chamber is buried inside a mountain, so which is called as Mount Akeno. So this mountain is where the chamber is within inside. It's a secured premises, of course. And why do we have to keep it here? It's because these neutrinos are very elusive, as we know that, and they actually don't interact with matter. But at the same time, these mountains will give us chances. There is no chances of other electrons or electromotive force or anything that could possibly affect the study of this materials, of these subatomic particles. So now this chamber, if you look at it, it's 41.4 meter tall and then 13.3 meters wide. It's a pretty large chamber, and this chamber has got few things in it. One is the central hut, which is the dome of the chamber, and there is a control room. This is where the scientists will monitor what is happening with the subatomic particles once it's entered the chamber. And then there is an outer detector, and then there is an inner detector. The inner detector is actually the reason why it is called as a golden chamber. So these inner detectors are actually 11,000 golden bulbs. So these bulbs are not like light bulbs. They are actually photosensitive photomultiplier tubes. So these are basically can detect even a very, very small emittance of light from some subatomic particles. So these are the photoelectric cells. And so these are lined along the entire chamber, and then in the bottom of the chamber there is actually water that is filled in. So the reason being is these subatomic particles, they tend to interact with water. So that is the reason they have water, and when it interacts with water it emits light. So that light can be captured by the photosensitive cells. So now these waters are not actually normal water. So they're actually around 50,000 tons of ultra pure water. So the difference is the regular water that we have for drinking has got a lot of minerals in it. So these pure water are actually UV screened, and then it's of no microbial activity, and then it doesn't have any minerals, and these waters are actually pretty dangerous. If you see, they are more it has got both the alkaline and the acidic properties, and so let's say if you actually put a little hair into it, the hair will actually bleach, and then if you actually happen to come in contact with that, you can actually suffer severe itching, and then might also leach some of your skin. So that's how much dangerous this pure ultra pure water is. And so now this chamber is actually sitting in a mountain, and this is on the western coast of Japan, and there is actually another portion of it where they actually generate these neutrinos, which would be captured by the Super-K. So this chamber sits, and there is another portion of it which is the J-Park, that is the NT280 neutrino detector, and it also produces some of the neutrinos as well. So this one sits around 295 kilometers on the other side of Japan. So this is on the east coast, and this is on the west coast of Japan. And then you can see that that's actually 1,700 meters below the sea level as well. And so now let's take a look at what's happening here, and then what's happening here. So first thing is, before we get to this one, so come with some of the basic things. You know what is a Big Bang, right? So first thing, the universe started with a Big Bang. So that means everything was so compressed into a little pinhead, and then suddenly it expanded and blown away, and the whole universe was created. From the time the Big Bang started, everything starts expanding and expanding and expanding to an everlasting expanding. Scientists say that after a point it will start coming together, and then there will be another Big Bang. So that's the sort of science stories. And so now after the Big Bang happened, people predict there is equal amount of matter and antimatter. So there is like matter is basically anything that you see, that you feel, that's basically matter. So antimatter is just another entity. It doesn't mean antimatter, so we'll come to that in another video. So they were actually in equal proportions when the Big Bang happened. But now, after the it's been several billion years probably after the Big Bang. So now if you look at it, you can see lots and lots of matter, but literally there is no antimatter. So scientists are still wondering what happened to the antimatter. So why it is so few, why it is not even able to detect it, why it is below detectable levels. So what is happening with that? So that's one of the major reasons people are going into this kind of stuff. So now that's a little story. So next one is, so in here, so in the J Park, what is happening is they actually getting this neutrino generated. So now how does it happen? So these neutrinos, most of these ones are actually comes from space. They comes from the cosmos, and when they actually comes from the cosmos, the detections are very hard to make it. It's because we don't know what time it happens, because it comes in all the time, and we don't know what quantity reaches our place and which is detected from which source. So a lot of these questions are unknown. So that's the reason they actually launch it from here, and then they study how much have come up here and what is the time frame and everything. So now if you look at here, so the main thing that happens is they actually beam a photon, a proton beam. So they actually launch a proton beam against two slabs of graphite, and these graphites, and then what happens is when they actually smash it together, it actually creates pinions. So these pinions are actually subatomic particles as well, and these pinions, and then what happens is decay into muons. So that's muons is actually one of the objects they wanted to study with. And muons, when actually goes through this second slab of graphite, it actually blocks some more protons as well, and then so the muons jump up beyond the graphite. So this is what happens up here. So this is, they called it as ND 280, which is near detection 280. So what happens here is when they actually release the neutrinos at this point, they tend to create some sort of a count of how much they actually sending it across to the super K. So they have a count. Let's say they have 1,000. So when it comes up here, so they will not be able to pick up all 1,000 of them. So whatever they could be able to pick up, they know that the quantities and the proportion they have picked it up. So they would be able to do some analysis based on that. So now if you see from here, so the beams actually travel from here to the super K, to the mountain. So now once it reaches here, so there is few things that happens here. So the very first thing is these neutrinos are high energy particles. So some of these high energy particles interact with the water. So when it interacts with the water, it actually replaces some of the electrons in the water, which is called H2O. So it reaches some of the electrons in the water atoms. So when it does that, the water loses the electrons. Then naturally what happens is it tries to bring into an equilibrium state by replacing the electrons and then coming to a stable state. When it does that, there is a small emittance of light. So that is the whole point. They actually aligning this chamber with a lot of these photosensitive cells, so they can actually pick the light that's getting emitted. Now the trick is the lights getting emitted are not going to be the regular lights. These light particles are too fast. They're actually faster than the actual speed of light. So the problem with that is, so when sound travels faster than the speed of sound, we have shock waves. So now the same way, when the light travels faster than light, we have another option, another thing, which is the Cherenkov radiation. So which is called the Cherenkov radiation. So these Cherenkov radiations are very hard to detect. So these detections are done by the photo multiplier tubes. So this is what the purpose of it. So now whenever there is a light emitted, so they will detect it and then they'll do the studies on top of it. So this is what happens in the super K. So now if you look at it, there is actually two types of particles they get to study. So one is the muon neutrinos, and another one is the electron neutrinos. So the muon neutrinos actually produces the muons, they decay and produce muons, and they will actually look like sharp rings. and then the electron neutrinos produce electrons. They look like diffused rings. So that's how they understand the difference between them. So this is all about it, guys. And then the next little updates from on this one is, so if you heard of CERN before, CERN, so that's actually another neutrino project which was there several decades, probably a couple of decades, and they're doing lots and lots of neutrino based research. And then India is actually investing 1,500 crores, that's Indian rupees, into making one of the world's biggest neutrino stations. So they're going to actually do a lot more research on that. That's going to be the biggest and most powerful magnet, and so that's going to be part of the that's going to be placed in the southern part of the India. The reason it is generally placed in the southern part of India is towards the close to the equator, which is better for the neutrinos to actually capture more of these neutrinos to do the studies. So that's the main reason. And people also been talking about saying that these neutrinos created by radiations and things like that, and so far there is no scientific evidence to prove that this is harmful to the humans or any living matter, because these are subatomic particles. These already go through our body right now as we speak, so they don't really interact with matter at all. So I don't think that this will have any impact on any living organisms. All right, guys, thanks for watching, and if you like it, subscribe to the channel. Thank you so much.